Okay, I think it's time to start. Isn't it pretty dead on right now? So yeah, welcome everyone. I'm so glad to see such a nice turn up. And hopefully you've seen a lot of cool talks already. Maybe some technical, some, very, what you call it, hard ones. So you really have to think about everything you're hearing. And then I would like to welcome you all to my talk, A Bird's Eye View of a Parser, where we'll take a step back and try to make it a bit more relaxing, high level, and not too demanding of you guys. But first of all, I just want to introduce myself. My name is Joakim, and I really like programming languages as a topic of their own. And by extension, I enjoy language theory and that kinds of stuff. So I've been this close into studying linguistics for fun. So that's the kind of guy I've become. I also like geese, so you can see that goose over there. You'll see a lot of this throughout the presentation. And this year, I even have permission from House, the developers of the game this goose comes from, to use this. So in order to honor this agreement, please do not pay me for this presentation, but come see me afterwards if you want a copyright infringement-free talk for whatever you want to hear about. So, why am I doing a bird's eye view? This is kind of like a series of talks I've started doing. So the second one so far, last year was in this very room, actually, last year, about compilers. And now we're doing parsers. And I just feel like whenever I talk to people, there's a lot of things we always take for granted, right? So last year there was compilers. People tend to use programming languages all the time, especially since many of us are probably developers, and we just write our code and don't really care about what happens as long as it's correct. But we don't really think about all the work that goes into making it correct, right? Same thing goes for parsers. They are everywhere, and we are kind of reliant on them, but nobody really gives them much thought. So I'm just trying to shed some light on all the things we take for granted. And because we're doing a bird's eye view, so high-level, abstract kind of introduction, there won't be many implementational details, so the practical use of this talk may be limited. If you want to write your own parser after this talk, and you're able to do so, it was probably not because of this talk. That was because you're a good developer, right? But if you would like to learn how to build one, hopefully I will give you all the building blocks and terms and names you can read about on your own. But instead, I'll give you the tools and names to reason about things. So maybe you get a syntax error. What does that mean? Maybe you have always wondered why people hate regular expressions and why C++ is hard to parse. And I'm actually not going to answer those two questions in depth, so that was kind of just a tease. So, since we just have an hour, we have to limit our scope a bit. So we'll keep it high level, and we'll look at what a parser is and what its goal is. And since a parser always operates in context of some language, we have to define languages and the different classes of them. So a parser for regular expressions work in the context of regular expressions. You can't use them for much else than regular expressions, right? So we have to know about the different languages that we can work with. And then finally, we'll take a look at some algorithms and their accompanying data structures that make this possible. So fortunately, the algorithms themselves tend to be really, really simple. But building the required data structure is often the hard part. And because of this, I find it kind of elegant, the interaction between algorithm and data structure. I've chosen to focus on the table-driven parsing algorithms. And in particular, we'll focus on two classes of languages called the regular languages and also the context-free languages. And if you don't know what that means, that's fine, because I will tell you later. So, what is parsing? Parsing is simply analyzing your syntax. And the syntax is what you write, the symbols you type on your keyboard, right? It's not what you mean, it's just text, right? As opposed to semantics, which is what you mean by the text you wrote. So a parser or in order to parse something, you only have to answer the question, is this input string, your input text, part of whatever language you want to use, or in the context you're working with. And as a intermediate step of answering that question, we often find the structure of the text. So we break it down and we find a structure, which is often a tree, which we call an AST, or an abstract syntax tree. So if parsing is syntax analysis, then a parser would be a syntax analyzer. So it's just a program that does this for us. And you use one every day. I'd argue everyone uses it, even though if you're not developers. Indirectly, of course, because all of your regular expressions need at least two parsers. One to parse the regex you write, but then it generates a parser for your input, so you can actually use your regex to match whatever you want to match. We have a lot of data formats that needs to be machine readable. So I dare say every single one of you guys have used a web browser. Web browsers deal with HTML, which is I call it a data format, but I suppose it's a markup language. But you get what I'm saying, right? And also, of course, programming languages. So last year, I did a similar talk, but on compilers. So this is a graphic I stole from my previous presentation, showing a simplified compiler pipeline. And this whole block is the compiler front end, which essentially deals with parsing your language. So you go from text to structured text, so you can actually deal with it. So this is what we'll be focusing on today. But I've kind of hinted towards that parsers simply validate strings. They answer the question if a string is part of a language. Although many of you typically associate parsers with a thing that lets you extract some piece of information from, I don't know, like JSON or some other data structure, right? And if one definition is not more right than the other, it just kind of depends on what you're working with and who you are. So a parser can, of course, do both, but the base task of a parser is to answer the question, is the string part of the language, yes or no? And to do so, you implement some algorithm that we'll look at later, which validates your input by finding some structure and, in some cases, building up your AST, your abstract syntax tree, so you get a data structure or a structured view of your text. And then when you have a structured view of your text, it's a real short walk to be able to extract whatever you want from it. So, or do some other processing. So the lines of where a parser ends is kind of blurry to me, so I'm just going to say that you can do both. But in this talk, I'll be focusing on just validating. But just know that when you have found a structure, it's easy to extract whatever you need from the text. Now, I've been talking about languages, that we are operating in the context of a language, and by that I don't mean English necessarily, or C++. I'm talking about like a formal language, but I'm just going to call them languages now. And they are simply a set of strings that are derived from a grammar using some symbols. So a grammar is pretty much just a list of rules that lets you rewrite some string into another string. And we're dealing with both non-terminals and terminals. So a non-terminal is something you can transform using a grammar. But a terminal is something that's processed, so it's going to be part of the final string. And, excuse me. So here's an example of one, which I just wrote up, made it up all just out of nothing. I've numbered all the rules, and you read them left to right. So the top one, number 1, says that your start symbol derives, that's what the : equal means, a greeting, a name list, and a punctuation. And I've used the convention that a word with an uppercase first letter is a non-terminal, while quoted symbols or lowercase strings are terminals. I think that was right, yes. So everything that has a capital first letter, you will be able to find on the left-hand side of the derive sign, so you can keep on processing them until you end up with only terminals. So after applying rule number 1, we will have greeting, name list, and punctuation, and then we can apply rule number 2 to turn greeting into the string hello, for example. And this is the recipe we use to be able to generate infinite languages, because how many C programs are there? There's an infinite amount. You can always write a new one, right? So we need some sort of generating device, and grammars are good for that. You don't need a grammar in order to define a language. I just really prefer to have a grammar in order to reason and discuss languages, because I find them to be much more precise and clear. And they're good tools, like I said, because you can start at the start symbol and just arbitrarily apply rules to end up with all kinds of strings that will always be valid inside of the language. You can never generate something that's invalid. Conversely, you can use the grammar to check if a string is part of the language. And we'll look at that in just a second. So for that reason, we'll only consider languages defined by grammars in this talk. So this is our grammar again. I'll just minimize it, and we'll run a little example just so you can see how it all works. So I realize it says input. That's kind of a wrong word, but our target string is welcome Joakim exclamation point. So by convention, we will start with the start symbol. So you can see a textual representation to the left, and we will build an abstract syntax tree to the right. That's the circle, the black circle over there. So given the start symbol, we can only apply one rule, which is rule number 1, and that kind of looks like this. So now you see the tree has grown, and we have some new nodes that we can further process. In the abstract syntax tree, all the circles are non-terminals, so we will need to process them further until they become squares. We only want squares as leaf nodes. So moving on, we can turn greeting into welcome by rule number 3, because our target string says welcome, so we just want to do it that way. At the same time, we only need one name, so rule number 4 says that the name list can become a singular name. So we pick that production, which turns it into something like this. And finally, we want to use my name, and that's rule number 7. So we turn name into my name, Joakim. And finally, we turn a punctuation into an exclamation point, because our target string had an exclamation mark in it. And that's rule number, let's see, 10. And that's a finished, how do you say it? It's a finished string. It's fully processed now. And this is also what's called top-down parsing. So congratulations, you all parsed a string. It's called top-down parsing because you were able to recreate the string by applying rules to a start symbol. We can go the other way. That's called bottom-up parsing. And I won't go through this as vigorously as I just did, but here the clue is to apply all the rules backwards. So notice how we start with the string welcome Joakim exclamation mark, and then we apply rule number 10 in reverse, which turns the exclamation point back into the punctuation non-terminal. And then we keep on applying our rules backwards. So Joakim becomes a name, and name becomes a name list, and so forth and so forth. And if we end up with only the start symbol, that's a successful parse. So that means this string is part of the language and is valid. And of course it can fail as well, like this, where I've given us a string, welcome Joakim, Alan. And we do the same thing, applying our rules backwards. But at the bottom here, we end up with a greeting and a name list, but no punctuation. So we're not allowed to do rule number 1 backwards and end up with a start symbol. This is proof that this string is not part of the language. Even though it looks similar, but it's not we can't derive it using our rules. So that's a short primer on grammars, which I really love. So I could talk forever about this, but we need to move on. But before we move on, I just want to note a thing on our input moving forward. Sometimes we prefer to use tokens over text when we parse. And a token is an abstraction, because we don't want to write a grammar that handles every single number. We just want to deal with the abstract concept of numbers, right? So we make a token called number. So by adding a stage before our parser called lexical analysis, we can do like the little graphic shows us. Take our input text and break it down into meaningful tokens and work with those instead. Because from the context of a parser, it's really not interesting if a equals 2 or if it equals 4, because they're just numbers, right? And a could have had any name, it's just an identifier. It doesn't even have to be an integer, it could be any type, right? So we can have tokens for all kinds of types, all kinds of identifiers, operators, numbers. So we don't have to support them all in our grammar, unless you have a good reason to do so. And this is a way to reduce some complexity in the parser, but you will add another stage in your parsing process, or before the parsing process begins. So that's a trade-off you'll have to think about if you're trying to make your own system, if that's worth it for you. And since we're working on languages, it's important to remember that not all languages are created equally. They have different expressive capabilities. So Noam Chomsky defined his Chomsky hierarchy at some point, which I've enjoyed using because it's actually quite informative. So we have this circle over there where the different names are subsets of each other. So you have the recursively enumerable languages, which are the most expressive of all. And then a subset of that are the context-sensitive languages. And then you have the context-free, which is even more restrictive, moving down to the most restrictive of all the languages, the regular languages. And the different expressive powers comes from different limitations on how we can format our grammar rules. And we'll take a look at that in just a second. So some of these are mostly theoretical, the most free ones. So recursively enumerable and context-sensitive languages aren't really seeing much practical use because we don't really have any good algorithms for dealing with them. But context-free languages and regular languages are seeing extensive practical use. So I'll just start with a little toy thingy. So we have a simple language consisting of just like a list of strings. That's it. So the little thought bubble with a couple of strings inside, that's our language. That's the only thing we find to be valid, which is kind of useless and impractical, right? It's easy to parse because you just do string comparison with all the elements of the list, but you can't really use this for anything. If you need to add a new string, then you have to manually go in and add it, right? And like we said earlier, how many C programs are there? There's an infinite amount, so you can't really express this using a strategy like this. So we can move to the realm of regular languages, which was the most restrictive of the hierarchy. Now we have a few rules. They look like this. And then we have a recipe for deriving all the strings of our language instead of relying on a list. So this language describes all strings starting with a single A followed by any number of Bs. Could be 0 Bs, could be infinite, which is equivalent to the regular expression down there, AB star. I just assume most of you are more familiar with regular expressions than grammars, so yeah. And this is expressive enough to describe an infinite language, because you can always add another B, right? Oh, and the epsilon down there means the empty string. So B, the capital B, can be derived into a lowercase b and itself, or nothing. That's how we terminate so it doesn't go into an infinite loop, right? So the limitations of a regular language lies in how the grammar rules are formatted. You can see that the B, or the non-terminal, is always at the right side of the production rule. So this is a right regular language. You can also have a left regular language, but you can never mix and match, and you can never have more non-terminals. So due to that, we can never create a language using a regular expression that has balanced braces or parentheses, which we need in programming, right? Whenever you do a function call and you have your parentheses to put in your arguments or whatever, you want that to be balanced, and we need to guarantee that. Regular expressions can't do that. We can try with a little parenthesis open star and parenthesis close star, but there's no guarantee that they will be the same amount, so they won't necessarily be balanced, and that's bad for us. So this is what leads us to the context-free languages. We have a bit more powerful rules now in our grammar. Notice how the non-terminal A on the middle line is in the middle. That's not allowed in a regular language, but it's allowed in context-free languages. So this grammar describes a language where you have some amount of opening curly brackets, a single lowercase a in the middle, and then the same amount of closing brackets. So it will always be balanced. It's impossible to generate an unbalanced string using this grammar. And this is what we use to describe syntax in our programming languages. This is enough. So this is where we typically reside, when we're parsing, I want to say, interesting texts like a program or a JSON file or HTML. But again, there are limitations, because a context-free language like this can remember to always close any opening parentheses, but you can't count them. So it's kind of a bad example, but if you want to reproduce the thing down there, where you have 3 opening parentheses and then 3 closing parentheses, and then the same amount of opening curly brackets, which are also balanced in order, we don't have the tools to do that using a context-free language. So for the next slide, where we look at context-sensitive languages, which is the next step up on expressiveness, we have a language that can represent this. I've replaced the parentheses with A's, B's, and C's because it's a little bit more readable, but it's the same concept. And also noticed the context sensitivity of this language. Q does not always derive to the same thing. It depends on the symbols before and after it. That's the context sensitivity thing of it, right? And if you don't believe me, here's n equals 3. But it's not really that important. Context-sensitive languages aren't really practical. So, moving on. A parsing algorithm is then, now that we know what a language is and how grammars work, and we know what our goal is, that means our algorithm will have to try and figure out which grammar rule to use or which production to use, right? And there can be many variants if you just Google parsing algorithm, right? However, they can be broadly split into many categories. There's the brute force approaches with backtracking and all kinds of inefficient things. I'm not going to talk about that. Don't find it too interesting. And then we have the categories of top-down parsing or bottom-up parsing, which we saw a brief example of earlier with the grammar that we did first downwards, and then we went backwards again afterwards, right? And then each class of language has its own algorithm and accompanying data structure to support that algorithm. And also whether or not we use a look-ahead. So that's how we can categorize all the languages. You also need to handle or report ambiguities. Since a grammar can be ambiguous, you can end up parsing one string in several ways. That's bad, because then we don't know what to expect. So a parser can't be ambiguous, because you need to disambiguate it somehow. or at least report an error, which is also a fair strategy. So C++ is ambiguous. That's why it's hard. That's one of the reasons it's hard to parse, and we'll see an example of that at the very end. But fortunately for us, the algorithms themselves are really simple. Building the data structure is the hard part. So we'll look at both. And starting with regular languages, which are closely related to our regular expressions. And in order to parse a regular language, you're simply doing graph traversal. So that's something I believe we've all done at some point, some pretty early in, I guess, our studies or careers. So that's pretty easy. And we have some predefined accepting state. And as long as we end up in that state, we're good. That's a successful parse. So that makes it a top-down parsing algorithm for the most part. And we need some finite state machine to be able to traverse. And that's pretty much it. You don't need anything else to support that. And it's really hard to be ambiguous about traversing a graph. But it's worth noting that a practical regular expression typically has more features than the regular languages from the Chomsky hierarchy. So, you know, your favorite regular expression library will probably have some features that are considered context-free or even sensitive. But we'll stick to the basic regular languages. So given a string like hello, you have a state machine like this, where you start in the start symbol, like always, and you want to end up in the double circle. That's how I denote an accepting state. And you can see between each state, there's a transition, an arrow, with a character on top. That means you need to consume that character in order to be able to take that transition. So we can see that we have an H, so we can move to state 1. And that's pretty much how the story goes. If we end up in the last state, which has a double circle, we're fine. But this was a really simple example. How about something like this, where our input is help, exclamation point, and our regular expression is hello or help. You can see that our start symbol has 2 H transitions, so how do we know which one to take? And the answer is you don't really have to choose. Being non-deterministic is fine, so we go to both at the same time. This is what I think I read somewhere, it's called set traversal, so you're traversing a graph while keeping a set of the states you're in at the same time. So now we're in states A1 and B1. And we can just look at our available transitions, which again is an E, and our input help has an E, so we can take that. Help then has an L in it, and both has an L transition, so we take that as well. But now, the A1, 2, 3, 4 track wants another L, while the B track wants a P. And we can't have 2 characters at the same time. And our input help has a P for us. So that means the top branch failed, but the last one passed. And then we keep on consuming, and we end up in the final state, which is a successful parse. And something like the star, the clean closure, introduces the concept of an epsilon transition, which is a transition you can always take no matter what. So for the regex AB star, which is the grammar we saw earlier, 1A and then any number of B's, we can consume the A, and now we have one transition that requires us to consume a B, or nothing and go straight to the goal. And that's fine, because we support having no B's at all. Or we could consume a B and loop here for a bit, keep consuming as many B's as the input has for us, and then move to the goal. So the parsing algorithm itself is kind of simple, but I've just given you all the finite state machines. So now we're building our own. And my favorite approach is using Thompson's constructions, which is pretty much like playing with Legos. You have your basic building blocks. This is consuming a single character. This is concatenating 2 sub-expressions, and then a choice between expressions, and finally our star. So you can just take a look at your regular expression, find the basic building blocks, and just put them together. So all the squares in these constructions are meant to be replaced by other sub-expressions. right? So I can look something like this. I've minimized it up there for reference, so you can still look at it. And our regular expression is A or C, followed by any number of Bs. So obviously there's a concatenation here, because we want first an A or a C, followed by any number of Bs. So we use the Thompson's construction for concatenation. Now I want to finish the A or C part, so I replace that square with the choice construction. And finally, we still have squares for consuming the characters A and C, so we apply the construction for consuming characters. And finally, we want to handle the B star, so we just replace the square with the construction for A star. And that's how you can build a regular expression finite state machine. So if you now start from the start symbol, you can see there's a lot of epsilon transitions. We can take them all. So we'll end up in the states right before we consume an A or a C. At that point, our input is still just one character, so we have to choose, is it A or is it C? We can't do both, that's impossible. And then, given that we find an A or a C, we can move on to the B star part of it. And we already see how that worked, so I'm gonna skip that. And that's pretty much what I have to say about regular languages. You just try to build your finite state machine, traverse it, and then see if you're in an accepting state, or if you ever ended up in a scenario where you did not have an available transition for the character you want to consume. So, context-free languages. Those were the kind of languages we use to represent programming languages, because they're expressive enough to let us describe all the different constructions we use in our day-to-day coding. Because they can remember, right? So every time you open a parenthesis, it can remember to close it, and if you, in your input, forgot to close it, it will throw an error, right? And for the basic algorithm of this, you have way more choices than for the regular languages. So you have your top-down and bottom-up algorithms, and inside of each of those two categories of top-down and bottom-up, you have different parsing schemes with different expressivenesses. So you end up with like a subset of context-free languages, given whatever you chose to do, which is smaller than all of the context-free languages, but bigger than the regular languages. So sometimes you have to either rewrite your grammar to fit whatever scheme you're trying to do, or just really think about which parsing scheme you want to use. So we have like LL family of parsers, you have LR family of parsers, and there's the recursive descent parser, which I will not cover. The two first ones, LL and LR, are table-driven, but the last one is pretty much just how you want to codify your grammar. So that's typically how you handwrite a grammar. Handwrite a parser. But it doesn't have that elegant connection between algorithm and data structure, so I'm not going to talk that much about it. So, since we're building the data structure for a table-driven parser, not going to consider recursive descent, like I just said. And some books say that context-free languages are equivalent to a push-down automata. I never found that definition to be helpful, so I prefer to just look at tables, honestly. So we can build a parsing table and then have an accompanying stack, and that will be everything we need to run our algorithm. In order to build our parsing table, we will have to compute two sets. So the first set and the follow set. These sets will tell us which productions we can use in any given, they will tell us which production we can use when looking at a particular symbol. So when we have computed those, we can make our parsing table, and the top-down family of parsers, the LL family of parsers, have the exact same algorithm. The only thing that's different about the different LL parsers is the parsing table. The same goes for bottom-up parsers or LR parsers. There's a bunch of different variants, such as SLR, LR 0 and 1, and then LA LR. But I'm not gonna talk too much about it, because the algorithm is the same. You can just swap out the table, and then it will be more or less efficient or expressive. So for the purposes of demonstration, I'll make an LL table, because LR tables are too big. They simply grow too much because they're more expressive than an LL table. So this is a little grammar I've just made up, which kind of is like JSON-ish. It's not really practical, but it accepts strings like this, which kind of looks like JSON and fits in a slide. That's the main part here. A little blunder I did was that it does not support having multiple objects. You can just pack in your one object in many, many different ways. I didn't think about that until it was too late. But it doesn't matter, because I can still use this for demonstration. And recall that we use some tokens here. So the key, key at the very bottom is a token, which represents all valid keys, and the same goes for value. So the first and follow sets. They're a set for each non-terminal symbol we have, so that we know something about them whenever we see them, right? So the first set answers the question that for each symbol, what's the first symbol that can appear when I expand it or when I derive something from it? So given some non-terminal, I can apply a rule on it, right? Because we have our grammar. And the first set answers the question, what's the first symbol that can appear? And then there might be several choices here, but we'll take an example. So given the key value non-terminal, it only has one rule. And that one rule always produces a key at the very start. So the first set of key value will always be key. That's a given. For something like an object, if you expand your object using the available productions we have, we can find that we can find, oh, that was a weird sentence. We can find that we'll see a opening curly bracket at the first, as the first symbol, or an opening square bracket. But there's also the key value list production, which is down there, which again derives into key value, and we already know the first set of key value. That was key, right? So this is an example on how you have to kind of traverse your grammar in order to figure out your first and follow sets. So this is the first set of an object. So if we do this for all our non-terminals, we gain a lot of information we can use. Same goes for follow. The follow set for a specified symbol tells us what can immediately follow it. And that's useful sometimes because some rules are just the empty string. So a non-terminal can, in practice, just disappear, right? So we need to know what can follow it. Because when we're doing predictions on which production we want to pick, if a production can simply disappear, we need to know what comes after it, so we don't get confused. So the follow set of an object is, in this case, kind of easy. We just look at where it's located on the right-hand side, and we can see that the follow set of an object are the closing braces. There's no other symbol that can follow an object. For a key value list, it might be a bit more involved, because it's only used right there. See that? So it's not immediately obvious what symbols can follow a key value list, right? But since an object can derive into a key value list, you get the same follow set as an object. So key value list and object share their follow sets. Now, given that we have successfully calculated all of our first sets and all of our follow sets, we now pretty much know what to expect for every single scenario. And when we know what to expect in every single scenario, we can just write that down in a table. Now this is where all the different parsing schemes differ. So I'll just give you the finished product instead of going through it in the interest of time. So this is the parsing table for the grammar we just saw. And you read it something like this. So we're working, that's our grammar for reference, by the way. So we're working on an object. And our current input is the opening curly bracket. When we're in this scenario, we know that this is the production we want to use. So if we end up in a situation where let's say we're working on a key value list, the key V list, and our input is still the opening curly bracket, you see that there's no entry. That's a parsing error. So the algorithm is short and sweet. We have our input, and we put a marker on at the start, so we know how far into the input we've processed, right? And then we have a stack. We initialize it with our starting symbol and the end of input. For some reason, literature always uses the $ for end of input, so I just use that myself. And then we simply compare our current input and the top of the stack, as where the two arrows are. If we're working with a non-terminal, which we are right now, so we're pointing at S, right? Then we pop it, and we push whatever rule we find from the parsing table. If there's no entry, there's an error. If the two arrows are pointing at the same terminal, that's great. We've proven that so far this is part of the language. So we increment our input marker and we pop it from the stack. If you're looking at two different terminals, that's also an error. And finally, if you can match the end of input, then it's an accepting state. Whew, okay, that was a lot, right? And it gets worse because we're going to do it, huh? Oh, I spent so much time on this. I hope this works out. So our current input is this character right here, the opening curly bracket, right? Think about that while I take a drink. Oh, sorry. And our top of stack is S, which is our start symbol. I just abbreviated it because we need to save some space. So we see that we find this rule right here. So we pop S off the stack right now, right? And then we push whatever we found in our table. And that's our first step. So we just keep on doing this. So now we're looking at the same input symbol, but we have a different non-terminal in our stack. So we see which rule should we pick this time. And now we have, what does it say, object inside of curly brackets. So we pop the root symbol and add whatever we found in our parsing table. Now we're at the fun little milestone because the two arrows are now pointing at the same terminal. So we can pop it off the stack and increment the input marker. So now our current input is a key, not the opening curly bracket, right? So we just keep on doing the algorithm and we see what we find in our table. And when we find a rule, we pop the old one and push the new one. And this just keeps on going for a little while, where we have a key and a key value. That's down there, which gives us that rule. So we pop key value off the stack and add the things we found in our table. Now we have a key in two places. The two arrows are both pointing at keys. So again, we can pop the terminal off the stack and increment the input marker. So we've successfully consumed some more input, and that's great. And what's even better is that we can do it again and again until we reach almost the end, where we have a closing curly bracket and the key value list optional. And we see that the rule we have is an epsilon, which again means the empty string. So we should pop the key value list optional off the stack, but it doesn't really make sense to push nothing, right? So we just don't do anything. So this is our current state right now, and then we have a final matching terminal, which leads us to the input marker being gone, and the stack only containing the end of input marker, which is an accepting state. And that's, I guess, how the cookie crumbles. That's how the LL parsing algorithm works. So the different varieties of LL parsing and also LR works in a similar way, except with different parsing table. Yeah. And that's what I want to say about context-free languages. So I find it to be very neat that whenever we're working with table-driven approaches, we have this static algorithm, right? The one I showed you on the slide, for example, or the graph traversal for regular languages. It's just static. It doesn't really do that much. The important thing is the data structures. And data structures can be generated, right? So if you write that algorithm once, and you write some logic to compute your data structures, you have a parser generator. So you'll have 3 parsers for life, right? You can even pre-compute them, so you save some precious resources. And that's what Flex does for regular languages, or Bison or Antler, if you guys are familiar with any of those. Of course, I'm simplifying, but this is the basic idea of a parser generator. And I think that's quite cool and elegant, to be honest. But there's a big but here, and that's there are complications, of course. I'm, painting a picture where parser generators are the way to go. Not really always the case. So table-driven parsing has its drawbacks, where it can oftentimes be better to just handwrite a parser using, for example, recursive descent. But it depends on what you're trying to do. If you're writing something like GCC, you wouldn't probably use a parser generator. You want to handwrite it because it needs to be as efficient as possible, and the language is not likely to ever change. The main benefit of using parser generators is that if the syntax is, kind of changing, kind of in movement, you just generate a new parser really fast. You don't have to maintain a big code base for parsing. And that's a really useful feature to have sometimes, but if you're just trying to make a JSON parser, JSON is not likely to change. Probably don't need a parser generator, unless you just feel like that's easier for you to use, which is also fine. But since we're doing table-driven parsing, that comes with a memory footprint. So if you're working on some constrained environment where memory is not really what you have to spare, you would prefer to be, compute intensive instead of memory intensive. Again, not a great use for parser generators. And like I said, the different LL and LR algorithms have some expressive limitations, whereas in something like a handwritten parser, you're writing the code yourself, so you can be as expressive as you want and need. And finally, there are ambiguities and conflicts that can appear. Some of them you can fix by just looking at your grammar. Others are harder to deal with. And I suppose many of us are C++ developers, so maybe you've heard of the most vexing parse, which is a famous example of an ambiguity inside of C++. Kind of looks like this. I think I stole this from Wikipedia, so don't hate me for code style. But in our main function right there, where we initialize our timekeeper, see what I put inside of the parentheses there? That's ambiguous. So when I tried to compile this, I think it was using GCC, it said parentheses were disambiguated, that's how we say it. The parentheses were disambiguated as a function declaration, which is totally not what I want, but at least it told me about it, so that's fine. And obviously this failed later on in the compilation, because putting a function declaration in there doesn't really make sense. So this is a famous example of how C++ is ambiguous, and how the parser employed a disambiguation strategy that I'm personally not happy with, because I don't know, I feel like this should be allowed and do what I thought it would do, but that's a different discussion altogether. So I always like to end my talks with this slide. If you're not going to write a parser, why would I even bother with this? And I like learning about things, and I think this is fun. But I realize that doesn't go for everyone. But if you have a good foundation in parsing, you have a good foundation of making developer tooling. And I also think that's kind of cool. So syntax highlighting, how would you do that? You make like your little regular expression FSMs maybe, match substrings of whatever lines you have in your editor. You can do formatting or linting because you have parsed your code and you have structured it as a tree. So you're free to rearrange it because you already have all the information, right? And all kinds of other code analysis tools. So, you know, even though you're never going to write a parser, I think it's still worth noting that they exist, and we should think about them from time to time. And that's it. Are there any questions? I am still the best speaker of all time. No questions. Awesome. So, no questions? Then I hope you all have a good day.